Good afternoon, sir. I'm Brian Rebolios, the next reporter. The union of a countable number of a countable set is a countable set. Proof: we consider a countable collection A sub 1, A sub 2, and A sub n of sets A sub I, each of which is itself countable. Thus, for each I, the set A sub I can be displayed in a sequence form as A sub I equals to A sub 1I, A sub 2I, and A sub ni. The theorem will become evident when a sequence is constructed in which all the elements of all the set A sub I appeared, because A sub 1 equals to A sub 11, A sub 12, A sub 13, A sub 1, and A sub 2, A sub 21, A sub 22, A sub 23, and A sub 2n, A sub 3, A sub 31, A sub 32, A sub 33, and A sub 3n. And the last one is A sub I equals to A sub I1, A sub I2, A sub I3, A sub In. Vacant for diagonal path indicated to list all the A sub ij systematically as a sequence A sub 11, A sub 12, A sub 13, A sub 14, A sub 21, A sub 22, A sub 23, A sub 31, A sub 32, A sub 31, and A sub 41. Every element of each set A sub I will eventually become encountered somewhere on the path. Hence, a 1-to-1 corresponds between the set of A sub ij in the set n of natural numbers is implied, where any element that is repeated can be deleted from the list when come to it in a second time. It is not hard to write down the actual formula giving the 1-to-1 corresponds from U A sub I to n being used in this process. In fact, one can easily show that the formula for the 1-to-1 corresponds is A of A sub ij equals to the quantity of I plus j minus 1 times the quantity of I plus j minus 2 over 2 plus j if I plus j is given, and also the quantity of I plus j minus 1 times the quantity of I plus j minus 2 over 2 plus I if I plus j is at. But the description of our listing is so simple that there is no need to use this implicit corresponds. So that is our formula. Corollary 1. The union of a finite number of a countable set is a countable. Proof: if countable sets A sub 1, A sub 2, and so on, A sub n are to be considered, we may use the theorem on taking A sub n plus 1, A sub n plus 2 to be the empty set. Corollary 2. The set Z of integers is countable. Proof: certainly the set N of natural numbers is countable. We display the set of all the integers Z equals to N U, the quantity of 0, minus 1, minus 2, minus 3, and so on, and minus n, to see that Z is a union of two countable sets. Corollary 3. The set Q of a rational number is countable. Proof: we consider the positive rational numbers, classifying them by denominator. The set of A sub 1 are 1 over 1, 2 over 1, 3 over 1, and so on, and n over 1. The set of A sub 2 are 1 over 2, 2 over 2, 3 over 2, and n over 2. This set of a sub 3 are 1 over 3, 2 over 3, 3 over 3, and n over 3. This set of a sub 4 are theorem. This set R of real number is uncountable. Proof. Let us assume that the theorem is false so that the real number form a countable set. Each innate subset of real numbers must then be countable by an earlier theorem. The subset we want to consider is the set of all real numbers x satisfying 0 less than x less than 1. Every such real number has a non-terminating decimal expansion such as 0, a sub 1, x sub 1, x sub 2, x sub 3, and so on, and x sub n, where each x of I represent a digit in the expansion that is 0, a sub I, 9. The computation is equals by decimal in which all the digits assume the value 9 after a certain point. Numbers like 0.36999 and so on, which is no different from 0.3700 or 0.37. To eliminate this ambiguity, let us rule out those expansion ending in innate string of zeros. In other words, we shall not identify the real numbers 3 over 100 by 0.37, but rather by 0.3699999 and so on. This set of real numbers between 0 and 1 being countable can be displayed as the set of a sub 1, a sub 2, a sub 3, and so on, and each a sub I has an innate decimal expansion. Let us say that 0, a sub 1, a sub 2, a sub 3, and so on is the decimal expansion of a sub I. We can write the element of set under consideration as the array. A sub 1 equals to a sub 11, a sub 12, a sub 13, and so on. A sub 2 equals to a 0, a sub 21, a sub 22, a sub 23, and so on. And a sub I equals to 0, a sub I1, a sub I2, a sub I3, and so on, where 0 is not less than but not greater than a sub ij, and 9 is not less than but not greater than for all I and j. Transcendental numbers. For the moment, we have been considering a division of the real numbers into two subsets. Those are rational and those that are not. It is also possible to think of another partition of real numbers into those that are roots of equation and those that are not. Definition. A number, real or complex, is said to be an algebraic number if and only if it is the root of algebraic equation. So a sub 0 x raised to n plus a sub 1 x raised to n minus 1 plus and so on plus a sub n minus 1 x plus a sub n equals to 0, where a sub 0 is not equals to 0, where n is a natural number and each a sub I is an integer. Theorem. The set A of a real algebraic numbers is countable. The initial half of Cantor's 1874 paper established the countability certain set, such as the algebraic number, which clearly seem at RST glance to possess this property. But it was the second half that contained the more profound result, and the RST great trump of set theory. This set T of transcendental number is the uncountable. The set of real numbers R equals to U and T. If it happened that T were countable, then R as the union of two countable set would itself be a countable set. This contradicts an earlier theorem, so that transcendentals must be uncountable. Before ending this digression, we should observe that although the matter of its transcendence was put to rest, there was still a concern with obtaining an accurate numerical value, for in 1853, the Englishman William Shanks 1812 to 1888 used the innate series for the arctangent function. Arctan x equals to x minus x 3 over 3 plus x plus 5 over 5 minus and so on, together with the formula pi equals to the 16 arctan, the quantity of 1 over 5 minus 4 arctan, the quantity of 1 equals to 239. The continuum hypothesis. Cantor having succeeding in proving the existence of innate sets with the same power and with different powers went on the attack New and Volder problems in the paper Contribution to Manifold Theory submitted to Grell's Journal in 1877 and published the following year. He showed that the point in a square clearly two-dimensional can be put in one-to-one correspondence with points of straight line segment. Clearly, one-to-one dimensional quite amplified for this paradoxical result, which seemed to clothe the concept of dimension. Cantor tried to discuss it with fellow mathematicians, but they treated the whole idea as an absurd, even with contempt. To establish the unit square S, denote by 0 less than or equal to x, less than or equal to 1, and 0 less than or equal to y, or less than equal to 1. And the interval 0 and 1 are equivalent, it is sufficient to match their point in one-to-one function. Give a point x, y of S. Let us represent x and y as an innate decimal. X equals to 0, a sub 1, a sub 2, a sub 3, and so on. Y equals to 0, y sub 1, y sub 2, y sub 3, and so on. Theorem. This set of points in the unit square has cardinal number C. The publication of Cantor's 1878 paper destroyed the feeling that the plane is richer in point than the line, and forced mathematicians to take a fresh look at the concept of the dimension, because Cantor's argument did not involve continuous mapping from one dimension to another. There was a theory of activity to show that the result failed under additional assumption that mapping between the spaces should be continuous, not until the appearance of an article by L. E. J. Brouwer in 1911. However, would there be established a rigorous proof of the invariance of dimension under continuous one-to-one mapping. Definition: let A and B be two given coordinal and A and B set with A equals to 0 times the quantity of A, B of B 0 times the quantity of B. Write A is less than or equal to B if there exists one-to-one mapping from A into B. We also write A less than B if A is less than or equal to B but not A equals to B. Thus, this definition, our intention that 0, the quantity of A, less than not or equal 0 times the quantity of B, where A is the subset of B, because if A is a subset of B, then the inclusion mapping A equals to B denote by I, the quantity of A equals to A is 1 to 1, so that we have of the quantity of A less than or equal to 0 the quantity of B in general, to show that 0 the quantity of A less than 0 the quantity of B must be demonstrated that there exists one-to-one mapping from A into B but not one-to-one mapping of A onto B. Note of caution: this is not equivalent the statement there is one-to-one mapping of A that is into B but not onto B. We're now in a position to tie up two loose ends. We have observed that the set of irrational number and the set of transcendental number are both uncountable, but we have assigned a cardinal number to either counter showed in fact that whereas the algebraic number of countable, the transcendental number have cardinality C, the power of continuum, because every transcendental number is irrational. The irrational numbers must then also have cardinality C for using T and I to denote the set of transcendental numbers and irrational numbers. You have chain of set inclusion. 12.3 The paradoxes of set theory. The early paradoxes. It has been said that the relationship between counter theory of set and mathematician was like the course of true love, never running smooth. About 1900, just when counter ideas were beginning to gain acceptance, a series of entirely unexpected logical contradictions were discovered in the fringe of theory of sets. Curiously, these were at RSD called paradoxes rather than contradiction, and regarding as little more than mathematical oddities. The feeling was the conceptual apparatus of set theory was not yet quite satisfactory constitute, and that some slight alteration of the basic definition would be set things right. Then in 1902, the British philosopher, mathematician, and social reformer Bertrand Russell, 1872 and 1970, offered paradox in which counters very definition of set seems to lead to a contradiction. This most notorious of modern paradoxes appeared in Russell Principle of Mathematician, established in 1903. Before we examine Russell paradox, let us observe that some sets are member of themselves, and some are not. This set of all abstract ideas, for example, it is an abstract idea, but the set of all star is not a star. Most set are element of themselves. Those that are tend to be far-fetched in description. With this in mind, we can formulate Russell paradox quite simply using the bare notion of set an element if and namely accept the Cantorian view that every condition determines a set, then it is obviously possible to consider the set of all sets that have property of not being elements of themselves. That is the set S equals to the set of A equals to A is a set, and A is not the element of A. Theorem: for any set, there does not exist a function mapping A onto its power set P of A. Proof: the general plan of attack is to show by an indirect argument that no such function exists. Therefore, we start with assumption to be refuted in the end that there is a function f of A equals to P of A, that is into P of A. This means that each element A, there is assigned a subset of f of A of A. Let us consider the set B denoted by B equals to the element of A equals to A is not the element of f of A. The set B is a subset of A, so that B equals to f of B. For some B element of A, recall that f maps and onto P of A. We now ask an innocent question. Is the element B a member of the set B? If B element of B, then by the very definition of the set B, we must have B not element of f of B equals to B, which impossible. On the other hand, B not the element of B equals to f of B implies that B satisfies the defining property of B, and so B element of B. This is also nonsense.